Hello, everyone. This is a new series on the mathematical structure of quantum mechanics. And originally, I was debating whether I should discuss group theory or linear algebra first. And I asked a lot of my friends who are actually experts in quantum mechanics. And they told me to discuss linear algebra first. And the problem with that is I find that a lot of fundamentals of linear algebra can be derived from group theory. And I feel that group theory is more fundamental than linear algebra. But I do see their point. They do go hand in hand. To define a representation, you need to define a vector space. And as a result, I decided to kind of go against their advice and talk about group theory first. And I will do it as follows. First, I will talk about group theory. Then I will talk about linear algebra. Afterwards, I will talk about representation theory. And finally, I will talk about Lie groups and the algebras. So, and after that, I will discuss more of the physics behind quantum mechanics as opposed to the mathematics. So in this lecture, I'm just going to talk about group theory and symmetries. So the outline of this lecture is as follows. First, I'm going to talk about the references that I will be using in order to discuss the mathematical structure of quantum mechanics. Then I'll provide a motivation behind studying group theory. Afterwards, I will define the fundamental structure of groups, namely groups, subgroups, homomorphisms, and isomorphisms. And I will give examples of all three. And finally, I will talk about their applications in physics. So first, I would like to discuss some references, and the former half is more of the standard reference that everybody uses, whereas the latter half are my personal favorites. When studying physics, especially quantum mechanics in undergraduate, there is no question that you will hear the book Introduction to Quantum Mechanics by D.J. Griffiths. And this book is, I guess, quite a good book for people who are starting off quantum mechanics, as before it goes into the mathematical structure like linear algebra, Dirac notation, it will first discuss the experimental motivation behind quantum mechanics, i.e. the experiments regarding spin, etc. However, in my opinion, I think it's more enlightening to discuss the theory, basically the mathematical structure, before discussing how they correlate with experiments. So you can see, because essentially in my philosophy in science is that we should make robust models. For example, make predictions using a theory, and then use experiments to test those theories and to check whether your theory has predictive capability. So I think it reflects more of science, how science should be done, and the element of discovery. But nowadays, science is sometimes not like that, right? Sometimes we make observations that contradict our theories, and then we try to modify our theories to explain those observations. So it really depends on your taste, but it's just my take. On the other hand, there are other two books that are also quite standard, namely Shankar's Principles of Quantum Mechanics and Sakurai's Modern Quantum Mechanics. These two books, I would say, are not really for beginners, but to be honest, in my opinion at least, they can be treated as beginners' textbooks. But they do have more advanced topics like the path integral formulation, discrete symmetries, etc. And many body theory. I can't remember if Griffiths has that, but for comparison, I think Griffiths is like 300-400 pages long, whereas Shankar is about 500-600 pages long. Sakurai is a bit shorter than Shankar, but well, let me discuss Shankar. For Shankar, has a lot of topics, and it's quite the perk of Shankar is that the discussion with and the connections drawn to the physics is quite good. But in my opinion, at least when I read it, it's a bit off-putting because it's quite wordy. On the other hand, we have Sakurai. Sakurai is a bit, I guess, I think it's shorter. It's similar to the length of Griffiths. I think it's like around the 400-page mark. I can't remember. But the point is that it is more, I guess, not quantitative, but the mathematics is more heavily emphasized, but the problem is the connection between the mathematics and the physics is not very clear, and a lot of the proofs in the book are not laid out in a coherent manner. You'll find in the book there are a lot of, oh, this is obvious, or the proof is trivial. It's left to as an exercise to the reader. So this book is definitely not a beginner's book because it's not beginner friendly. It doesn't outline everything. It doesn't spell everything out. So it's a standard book though, but it's decent. But the latter half are my personal favorites. So the first one that I would highly recommend, it is my favorite quantum mechanics book. It is Balantine's Quantum Mechanics, a Modern Development. And this one was recommended to me by my research supervisor when I told him, oh, I wanted to learn quantum mechanics and I'm struggling a bit. And he told me that this book was very, very good. And I think when I went to Caltech to do some research, some people also recommended this book to me. And I found it really good because it's similar to Shankar and Sakurai, but it has a good balance of both. Namely, Ballantine draws a very clear connection between the physics and the mathematics. Excuse me. And additionally, a lot of the proofs here are spelled out quite clearly. For example, when they use a particular formula to derive translations, for example, they tell you, oh, I'm using the Baker-Campbell-Hausdorff formula or something like that. Additionally, Ballantine has a very nice discussion on the connection between Dirac notation and dual vectors and vectors and inner products using Ries's representation theorem. And they also have quite a nice discussion on Hilbert spaces and the postulates of quantum mechanics. So this book I highly recommend because it's comprehensive, mathematically rigorous, and draws a good connection between mathematics and physics. So I really like this book. The other book that I highly recommend is Voigt's Quantum Theory, Groups and Representations and Introduction. But don't let the name fool you. When they say an introduction, it is really not an introductory textbook. This book is based on a graduate level, I'm not even sure if it's a physics or mathematics class, but it's a graduate level class on quantum theory at Columbia University. And since Voigt is part physicist, part mathematician, this book is very, very rigorous. So, but what I like about this book is that it starts off with the very fundamentals. Basically, he starts up talking about groups and representations, then moves on to linear algebra and draws the connections between the two, and eventually talks about how they connect to different physical systems like spin, talks about the symmetries, etc. So I also really like this book, but it is definitely not a beginner's book. It is considered quite rigorous and I wouldn't recommend it to anyone who's starting off the subject. On the other hand, the next book, it is also quite mathematically rigorous, but it is something that I can recommend to beginners. It is Chang's Mathematical Structures of Quantum Mechanics. And funny story about this is that this was actually before wanting to start off my career as a physicist. When I was 18 or 19, I picked up this book, and this was the first book I picked up to learn quantum mechanics. I didn't search up, oh, what's the best quantum mechanics book? I just went to the library, and this was the first one I picked up. And I didn't see Griffith's Shankar Sakurai yet. And this book, I guess, has left maybe I'm biased, or maybe it's something that has left a deep impression on me. But I found that the explanation of the mathematical structure quite clear. I understood what vector spaces were. I understood what dual spaces were. It made me understand the correlation between a Cauchy sequence, its convergence, and a Hilbert space, and why we need this in order to do quantum mechanics. It taught me basically how the operators act, basically the adjoint operator, the inverse operator, why the inverse operator is unique, why some operators are unique, and it also showed me some things like some cool tricks, like how the projection operator is idempotent, and how how operators are bounded. So this book is quite good. And I don't know if you can put it into perspective, but at 18 or 19, you don't not exposed to that much mathematics yet this book can clearly introduce those topics in a quite clear manner. But the problem with this book is, at least in the copy that I picked up when I was 18 or 19 years old, was this book does have a lot of typos, and which is not good. But the problem is, but the good thing is, I guess, when you read this book, you can see the typos quite clearly. You can clearly see that, oh, this is definitely a typo. It's not something that I'm missing. So this book is still, I think, quite valuable. And the final two books I rarely use, but I would still recommend, because they are very similar to Voigt's book in the sense that they are very, very mathematically rigorous, as you can tell by the name Quantum Theory and Quantum Mechanics for Mathematicians by Hall and I'm going to pronounce his name on Tak Ha-Gan. And these two books are very similar, but I guess the way that they introduce the topic is different. So Voigt, in his book, introduces the concept of groups, representations, and linear algebra before talking about their relation to classical mechanics, and then how we can and the relationship between Poisson brackets in classical mechanics and Dirac brackets in quantum mechanics, basically what happens when we quantize and add h bar. But in Hall and in the other two books, basically what they do is they motivate classical mechanics first and then talk about the mathematics later. So but they're still very good books. But I would, if you ask me to recommend a good book, I'd say Ballantine is number one, then these two, and then these other two are also very good. So these are the references that I'll be using when talking about the mathematical structure of quantum mechanics. So before talking about quantum mechanics, I guess we want to talk about what group theory is. And to do so, maybe I should motivate group theory. And the reason for studying group theory is that groups are the language of symmetry. And usually physics problems are very, very complicated and hard to solve. And to alleviate the pain of fully solving the complex problems, we can exploit some symmetries to make the problem easier. For example, in electromagnetism, we would like to use Gauss's law. This is probably something you're more accustomed to, right? When you're maybe first or second year physics class, you would like to exploit geometric symmetries in order to solve for the electric field, the electric potential, etc. And to do so, to use Gauss's law, we would like to exploit some kind of symmetry. So for example, when we derive the electric field for a cylinder, of a charged cylinder or a charged sphere, we exploit rotational symmetries. When we derive the electric field for a charged infinite plane, we would like to use translational symmetries, and that's how the Gaussian pillbox basically works. But what's nice is that all these symmetries can be generalized into one formal language, namely groups. And you may think that this is a topic only used in simple physics problems, but no. For more advanced topics like particle physics, group theory is absolutely indispensable. Let me give you one good example. For example, the reason why we can explain there are a certain number of gauge bosons. And for those who don't know, gauge bosons are the particles that mediate the four fundamental forces. So we have, for example, the one that we're probably most accustomed to is gravity and electromagnetism. I'll talk about gravity at the end because that's the most complicated one. But electromagnetism is mediated by the photon. So light mediates the force of basically mediates the force between electrons and positrons. The next one we have to talk about is the weak force. So the weak force is mediated by W and Z bosons, and they're the forces responsible for decay processes like beta decay. Next one is the strong force, probably something you're not really familiar with, but the reason why particle accelerators require such high energies is because we need to overcome the strong force, which binds the quarks together in the nucleus. And this is basically the strongest of the four forces within a certain distance. Once you invoke something like asymptotic freedom, they become very, very weak. So the final one is the gravity, and we have not found the force, the particle responsible for mediating the gravitational force. We predict it is a massless spin 2 particle known as a graviton, but we still have not found this yet. And we can explain for these 4 fundamental forces how many particles are in each group. So let's talk about, because in group theory, the generators of the SUN group tell you the number of particles. So for electromagnetism, so basically the U1 group, there's only one generator. So basically there's only one kind of photon. For the SU2 group, so how we find the number of generators is n squared minus 1. So SU2, so n squared is 2, 2 squared minus 1 is 3. So there are 3 W and Z bosons. So there's Z0, W plus, and W minus. The third one is the strong force, and the strong force has a symmetry group SU3, and we know that there are 8 colors in QCD, and this is why there are 8. So basically, SUN, n is 3 squared minus 1 is 8. So this is the generator of the this tells us how many particles there should be for the strongs. For the gravitational force, I actually have not done deep research into how many the generator. I don't know what symmetry group SUN as the gravitational force should be. In principle, it should also follow a similar trend. It should be the Lie group SUN, and maybe I didn't explain what SUN is. SU stands for special unitary group, and it is the set of all matrices with determinant 1, and basically it's the matrix times its matrix adjoint is also equal to the identity. So that's what's a special unitary group is. And so this basically explains how many particles we have in the standard model. But what is interesting is this is not the only group. So basically, you know that there are other particles like fermions. So for fermions, we know that there are many types of fermions, but they're generated by a completely different type of group, which is namely the SO groups, the special orthogonal groups. So the special orthogonal groups tell us how many fermions there are of each class. And similarly, there are other particles like the Higgs particle, which is a scalar boson, which is generated by a completely different class of symmetries. I can't remember. It's some kind of symmetry where we combine the SU, SO, and etc. So this is, or maybe multiple SU symmetries. So this is a virtual particle physics. We exploit the symmetries in order to determine the number of particles. So now that I've motivated group theory, maybe I should talk about what a group actually is. So a group is simply a non-empty set with a binary operation where I denote by dot that acts on 2 elements in the group such that they follow the following axioms. These are called the group axioms. So the first axiom is called closure. So basically we have 2 elements in G, such that the binary operation x dot y is also in G. Next, we have the associativity axiom. So basically, x dot y dot z, there should be no distinguishment between whether we operate on x dot y first or y dot z first. And maybe we can do an example if we treat the binary operation as a scalar addition. So x plus y plus z, there should be no difference to whether you do x plus y first or y plus z first, and the final outcome should be exactly the same. The next axiom it must satisfy is the existence of an identity, and there must be a unique element such that E operated on this element yields the element itself. So in the case of addition, 0 must be the identity, because you add a number by 0, it yields the number itself. So 0 must be the identity. And finally, with an identity, there must be also an inverse. Basically, an operator so basically we have another element, x to the minus 1. If you operate this on x, this should yield the identity. So in the case of addition again, if we have positive number a, if we want to get 0, we have to add by minus a, which in order to achieve this. So minus a is the inverse of a and vice versa. And one final note is that groups come in 2 different types. If the groups commute under the binary operation, then the group is abelian. If not, the group is non-abelian. And this concept may be difficult to grasp at first, but I will do some examples to demystify these kinds of these abstract concepts. So let us look at an example of a finite abelian group. So a finite group is a group with a finite number of elements. So let's consider the 6 roots of unity. So basically, 6 roots of unity lie on a hexagon within the circle of the set of all complex numbers of modulus 1. So when we look at this we can clearly see that the 6 roots of unity is a regular hexagon. So what kind of symmetries does this have? Well, you can rotate the hexagon one way, you can reflect the hexagon. So in this case, let us consider a rotation about one direction. So if the nodes here, let's say these are not labeled, if the nodes are completely indistinguishable, then there's always a symmetry when you rotate the hexagon by 2 pi by 6, which is pi by 3. So you rotate by pi by 3, you'll yield the hexagon in the same shape. So you can't, so basically close your eyes and then rotate the hexagon by pi by 3. If you open your eyes, you'll see the same thing. So this is what happens when you don't distinguish between the nodes. But if we do distinguish between the nodes, if we rotate the hexagon, basically, if I close my eyes, rotate the hexagon at pi by 3, and the nodes are distinguishable, what will happen? Oh, you will see that Z1 will move here, Z2 will move here. So this is not the same configuration. So what kind of symmetry does they have? Okay, so in order for it to be exactly the same, you need to rotate it exactly by 1 revolution. Close your eyes, rotate it by 1 revolution, and you don't see any difference once you open your eyes. So if the nodes, as mentioned before, if the nodes are unique and distinguishable, then to permute the nodes, we can rotate the hexagon by pi by 3. And to do this, for the 6 roots of unity, we can just simply multiply by e to the I n pi over 3, where n is some arbitrary integer. So let r to the n equals e to the I n pi by 3. However, since e to the I pi has a periodicity of 2 pi, then there exists only 6 unique elements. Well, hence set is 1 r, r squared, r cubed, r to the 4, and r to the 5. So basically why there's only 6 unique elements is that if we rotate it by r to the 6, let's say, then we get 1 full r to the 6. So if we substitute n equals 6 here, we get e to the I 2 pi. But that means we just rotated the whole thing by 2 pi. And this is exactly the same as not rotating it by symmetry. And therefore it's degenerate with 1. How about if we put n equals 7, so 7 pi over 3. But remember, this is the same as rotating it once by pi over 3 and then 1 whole revolution. So this is degenerate with r. So any other combination would be degenerate with any discrete rotation of pi by 3 would be degenerate with one of these. So these form a group under scalar multiplication. So we can see that clearly. So here I didn't check the closure property, but let's check it very quickly. So the operation of 2 elements in the group should yield another element in the group. So let's check this, right? So 1 by r should yield r by r yields r squared, r by r squared yields r cubed, r times r cubed equals r to the 4, r squared times r squared also equals r to the 4, r squared times r to the 3 is equal to r to the 5. Then you see what happens when we do r3 times r3, right? We get r to the 6. But remember, this is also degenerate with 1. So it would yield this. How about r to the 3 times r to the 4? That would yield r to the 7. But then that is degenerate with r. So every single combination where we do a scalar multiplication between 2 elements in the group yields another element in the group. So this is a group. So this is a closed group. So we can also clearly see that it is associative. So let me do one example, and then I will tell you that this works for every single element in the group. So let's say we have r times r squared. So if we do r times r squared first, we get this. Since we can add, so in exponentials, we can add the indices. So we get this, and we get e to the I 4 pi by 3. So if we do the same thing where we act r and r first, we get these 2, and then we get I pi over 3 times this. Then we also get I to the 4 pi over 3. And the reason why this works is because scalar multiplication is associative. And when we multiply two things together, we also add their indices, and scalar addition is also associative. So the operation is also associative. And you can easily check every single element in this group satisfies the associativity property. So 2 out of the 4 axioms are satisfied. So we can also see that 1 is the identity, because any scalar multiplied by 1 yields the scalar itself. So 1 is clearly the identity. So if we go back here, 1 times r must be r, 1 times r squared must be r squared, 1 times r cubed must be r cubed, etc. So 1 is the identity. So to show that every element in the group has an inverse, we let r to the n and r to the m be elements in the group, and recall that an inverse is defined such that a binary operation of 2 elements in the group yields the identity. So hence, for G to be a group, and if Rm is the inverse of Rn and Rn is the inverse of Rm, then they should satisfy this property where the scalar multiplication is equal to 1. So we can see that this condition is satisfied if n plus m is equal to 6l, where l is an integer. So basically, every element in the group definitely has an inverse. Moreover, we can also check one more property, right? We've already proven that this is a group, but to show that this is an abelian group, we have to check whether multiplying 2 elements together would yield different results if we swap the order. And it's obvious that it does not affect, the order does not affect the result, because scalar multiplication is commutative. Basically, 2 times 3 is equivalent to 3 times 2. So this automatically tells us that the group is abelian. So last time we looked at a finite abelian group. Now let us look at an infinite abelian group. So an infinite group basically is a group with an infinite number of elements. So what more can we, well, you can think, oh, what kind of set has an infinite number of elements? One is the real numbers. So we can see that this forms a group both under scalar addition and multiplication. So it is clear that, well, let us check closure again. So this group is clearly closed because the addition of 2 real numbers must also yield a real number, and the multiplication of 2 real numbers must also yield a real number. If you add complex numbers, then it will be complex, but we're only considering the set of real numbers, so this is fine. So the group is automatically closed. It is also clear that the addition and multiplication are associative. So we can check this property, right? So let's say we have 3 real numbers. So let's make it simple, 1 plus 2 plus 3. So if we do, in this case, if we do 2 plus 3 first, 5 plus 1 is 6. How about this one? We do 1 plus 2 first, 1 plus 2 is 3, 3 plus 3 is 6. So this would yield exactly the same result. So therefore, they're associative. How about multiplication? So let's do 2 times 3 times 4. 2 times 3 is 6, 6 times 4 is 24. And then we have this side is 3 times 4 is 12, 12 times 2 is 24. So they're exactly the same on both sides. So we can easily see that scalar addition and multiplication are associative. And in the addition, but in the next case, there are differences between the inverse. So basically, in the addition case, we can clearly see that 0 is the inverse, because any scalar added to 0 is equal to the scalar itself. But in the multiplication case, this is completely different. So let's assume that it is the inverse is also 0. A times 0 is 0, not A itself. So therefore, it can't be the identity. In this case, the identity is 1, because 1 times any scalar is equal to the scalar itself. So in the addition and the multiplication case, the identity is different. Next, we have to check what the inverse is, and with different identities, there should be different inverses, right? So in the addition case, for any positive number a, the negative number, so negative a will be the inverse, because the sum needs to yield 0. And if we have a positive number a and some other number b, for the for the result to yield 0, B has to equal negative A, and A has to equal negative B, and vice versa. So they're inverses of each other, and thus for any positive number, its negative counterpart is the inverse. In the multiplication case, it's a little bit different. So we know that the inverse is 1. So for any positive, well, it doesn't have to be positive, for any number on the number line, the inverse is its reciprocal, because A times 1 over A is always equal to 1. So these two have different inverses, and we can check that this is both addition and multiplication are commutative, because, well, let's say in this case 1 plus 2 plus 3. If we swap the order of 2 plus 2 and 3, right, we still get 5, and 1 plus 5 is still 6. So the result does not change if you swap the order of the operation. So here, basically, we have an infinite abelian group, and this group is a special kind of group. It is called a field, and I will discuss about fields in more detail in the next lecture when I discuss a vector a vector space, because I have to define a vector space on a particular field. So this is basically an important example that we need to remember for next time. So after looking at abelian groups, let us now look at non-abelian groups. So an example of a non-abelian group, a finite one at least, is the unit quaternion. So I denote by H hat, and it includes the elements plus or minus 1, plus or minus I, plus or minus j, and plus or minus k. And I put a hat on them because they can be thought of as the unit vectors that are orthogonal to each other on a Cartesian plane. So when you do vector calculus, you typically write ijk, and basically k can be represented as the z direction, j can be represented as the y direction, and I can be represented as the x direction. So it can be shown that this is a group under quaternionic multiplication. And to see this, let us look at a multiplication table. So to read a multiplication table, the first element must be operated on the row, and the second one on the column. So we do 1 times 1 is 1, I times I is minus 1, j times I is minus k, etc. So what can we do here to prove closure? So we check every single combination. So 1 times 1 must be 1, 1 times I is I, 1 times j is j, 1 times k is k, and they all lie within the set. I times I is minus 1, so it's in the set. I times j is k, which is also in the set, etc. So the closure axiom is satisfied. The next one we have to check is associativity. So a well-known result in a well-known result is that I squared is -1, j squared is -1, k squared is -1, and ijk is -1. So let's do the ijk case. So basically, there should be no distinguishment between operating ij first and jk first. So let's do I times j, that yields k. K times k is -1, so that works. So let's do j times k first. So j times k is I, and then we do I times I times I is -1, so they yield the same result. So there's no problem with no problem with doing ij first or jk first. Let's do another example. Let's do jki. So we can do jki. Okay, so jk first. So j and k yields I. I times I is -1, so that works. Jki, so we can do jki, so we do ki first. So k times I is j times j is -1, so it satisfies the associativity property. And we need to check this for every single element in the group, and we can see that this is satisfied easily by checking. The next one we have to check is whether there's an identity, and we can clearly see that 1 is the identity, because 1 times 1 is 1, 1 times I is I, 1 times j is j, 1 times k is k. And if we do it here, if we swap the order, right? So we do 1, so j times 1 is I, 1 times 1 is 1, I times 1 is I, j times 1 is j, and k times 1 is k. So 1 is clearly the identity. So now we have to check what is the inverse. And I told you before that I squared is -1, j squared is -1, k squared is -1. So -1 is just -1 times -1 is 1, right? So basically, the inverse of I is simply minus I. So because we just multiply by -1, right, to get +1. So -I is the inverse of I, -j is the inverse of j, -k is the inverse of k. So this is quite simple to check. And the inverse of 1 is just 1 because the inverse of the identity is just the identity itself. So that's trivial. And finally, we need to check, sorry, we've already checked that this is a group, but we need to check whether this is abelian or not. So we can kind of see that it's not, because we can do I times j, that yields k, right? But what happens if we do j times I? J times I is equal to minus k. So we can see a clear thing here. So basically, operating I times j yields negative j times I, which means that the commutator is non-zero, but the anti-commutator is 0. So basically, the sum between I, j, and ji is equal to 0. So this has some other applications in. So in quantum mechanics, we usually use commutators to check whether two physical quantities can be measured simultaneously, but anti-commutators have a little bit more relevance in things like Clifford algebras and etc. So this is this is quite nice, because this will have some, when we discuss Clifford algebras later, this will be a topic of relevance. But we can clearly see that this is a non-abelian finite group. But we can generalize this group to general quaternions, basically where we have A plus BI plus CJ plus DK, where A, B, C, D are real numbers. And we can see that this is clearly an infinite group. And basically, these satisfy similar properties of this finite group, but we have an infinite number of elements. So this will be an infinite group that is non-abelian. So now that we've discussed groups, let's discuss another structure called subgroups. So let H and G be groups such that H is in the subset of G. Then H will be a subgroup of G if H and G are groups under the same binary operation, this stop. In other words, if A and B are in H, then A dot B will be in H and also in G. The identity will be in H and also in G, and the inverses will be in H and also in G. Then H is a subgroup. Now we need to check that, well, basically we don't need to check, but this is another property of subgroups, is that let G be a finite group and let H be a finite subgroup of G. So now let this quantity be the ratio between the orders of G and H. So the order is basically the number of elements in that particular group. So if when we divide the order of G by order of H, we should find by Lagrange's theorem that that this quantity should be an integer, a positive integer, meaning that H is some integer multiple of G. And a more general definition of a subgroup is that for infinite groups, the order of G must be simply greater than the order of H. So this is a good definition for a subgroup, at least. So what are examples of subgroups? So let us look at the previous examples that we've stated already. So G is the group that includes the roots of unity, and U1 is the subgroup. G is the subgroup which includes the roots of unity, and U1 is the group of all complex numbers with modulus 1 under scalar. So these two form a group under scalar multiplication. And we can see geometrically what this corresponds to is that any polygon on this, any regular polygon on the circle will be a subgroup of the circle itself. So we can see the red circle. So this has 6 roots of unity. So the hexagon is because what happens is if you add extra nodes or extra edges, what happens is let's say this is an octagon, right? But an octagon will still lie on the circle. And if you add an infinite number of nodes, what happens is it will converge to the circle. So the the roots of unity are a subgroup of a group called U1. So, sorry, I went too far. So another example when we talk about the real numbers is that the set of integers are a subset of something called the rational numbers. So the integers are just numbers like 1, 2, 3 with 4, 5, and the negative ones. So basically they have no fractions in them. But the rational numbers can include fractions like 1/7, 2/3, etc. So under addition, the natural numbers are even under addition and multiplication, actually, the integers are a subgroup of the rational numbers. So basically, the rational numbers, on the other hand, are a subgroup of the real numbers under multiplication. So in summary, the integers are a subgroup of the rational numbers, and the rational numbers are a subgroup of the real numbers. So this is quite nice. This is another example of a subgroup. And in a physical context, what a lot of I did read about this the other day. What we can think of is that the natural numbers. Oh, sorry, this should be. So this is the natural number. This should be integers. This should be z. So there's a mistake here. This should be z. This should be z as well. So these two should be z. But it doesn't really matter. So what we can think of is that the integers can be thought of as discrete translations on a crystal lattice, whereas the real numbers can describe the continuous translation on a crystal lattice. So this is another physical way of thinking it. The next one that we talked about was the uniquaternions, and we already discussed the infinite group and the finite group. And the set of uniquaternions is a subgroup of the quaternions under quaternionic multiplication. This is quite obvious because the uniquaternions only consider plus or minus the absolute value of all I, j, k, and 1s, but the quaternions is more general. It includes any scalar multiple in front of these and the addition of the two I, j, k's and 1. So this is a larger group. So basically, we can see in this example, Lagrange's theorem is satisfied as the order of this subgroup is less than that of the group. So now that we've just discussed subgroups and some examples, let us discuss homomorphisms and isomorphisms. So the map F of F from some group H to G is a homomorphism between H and G if the following is satisfied. So basically, we have a binary operation in, let's say, H, and we have some binary operation in G that's such that this is satisfied. And basically what this ensures that structure, so this equal sign ensures that the structure of both groups are preserved. And what happens is that we can interpret the left-hand side of equation 5.1 as the product of A, there should be a dot here, but it doesn't really matter. So A dot B in H, and it is the image of F on G. And the right-hand side of equation 5.3 can be 5.1, sorry. The right-hand side of equation 5.1 can be interpreted as the corresponding image in G and its connection between the product of their images in G. So if the homomorphism is 1-to-1 and on-to, or in other words, if it is injective and surjective, then it is bijective, and then this is called an isomorphism. So let us look at examples of homomorphisms and isomorphisms. So one example of a homomorphism is that let's consider the U1 group. So this is an angular representation of the U1 group where C denotes the complex plane, and we can see that any point on this unit circle represents the set U1. So I obtained this picture from Peter Woit's book on quantum theory. So let us consider the map F from the real numbers to the U1 group. So what kind of connection are we seeing between the two? So let the map F of theta be equal to e to the I theta. So additionally, let us consider the scalar addition in R. So if theta 1 and theta 2 are real numbers, we can just add them here. So here, let's say this binary operation can be replaced with an addition. So we get e to the I theta 1 plus theta 2. Now we consider the scalar multiplication in U1. So basically this star can be replaced with a dot or a scalar multiplication symbol, and we get e to the I theta 1 times e to the I theta 2. But for scalars, the multiplication of exponentials is equivalent to adding their indices. So basically, equation 5.2 and 5.1 are equal. So consequently, this equation is equal to this. So this f of theta 1 plus theta 2 is equal to f of theta 1 times f of theta 2, which implies that the set of real numbers are homomorphic to u1. However, since f of theta plus 2 pi is equal to f of theta, namely e to the I theta is periodic about 2 pi, then it is a many-to-one function, and thus it is not one-to-one, and hence f is only a homomorphism, but not an isomorphism. So let us look at an example of an isomorphism. So let us consider the two-dimensional rotation matrix. So you've probably seen this before in linear algebra and maybe multivariable calculus. And this matrix is part of a more generalized group called SO2, which is the set of n by n matrices where A times the transpose of A is equal to the identity, and the determinant of A is equal to 1. So let's say that this is A, right? If you multiply this by the transpose, you'll find that it equals to the identity. And here you can clearly see that the determinant is 1, because cos times cos is cos squared, minus sine times minus sine is cos squared plus sine squared, which is equal to 1. So, but I will discuss the SO3 groups when I discuss the algebras more. Now consider the map. Oh, this should not be a T. This should be a 1. Sorry, this is another mistake. So let's consider the map G of U1 to SO2. So basically what will happen is that let us consider that G of theta is the same as F. So E is equal to E to the I theta. Now recall that Euler's formula states that E to the I theta is equal to cos theta plus I sine theta. So to see the isomorphism, we need to establish the relationship between G of theta and R of theta. And recall from, I guess, the lecture on optics where I talk about the Jones polynomials and the Jones polynomials. Basically, we introduce this minus basis where it is we take e to the x minus I e to the y, and then we multiply by this factor to normalize it such that the length is equal to 1. And what happens is that we can also, this is called a bra. So if we take the ket is essentially the dual vector of the bra. And I have not described what vector spaces and dual spaces are, but I will do that in the next lecture when I talk about linear algebra. This is why I say I was debating between whether I should do linear algebra first or group theory first. And this is one reason why. And this is so, but we can think of the dual space as simply the transpose of the vector and then take the complex conjugate. So then we can see that G of theta is equal to R of theta acted on the bra and the kets. So from this, we see that the transformation from G theta to R theta is simply acting the bra on the left and the ket on the right. And we can see that, well, now let us consider scalar multiplication or addition in U1. So if we add the two together, we get e to the I theta times e to the I theta is equal to this. So what happens is we get the product of two cosine and sine functions, and we get this factor here, so cosine. So we get this. And now let us consider matrix multiplications in SO2. So we do, so let us treat this as a matrix multiplication operator. And what we do is we do this. So if we have this kind of multiplication, we can factor the bra on one side, the ket on one side, and just multiply the two rotation matrices. We get this. And when we actually multiply the bras and kets, we find this relation. And we can see that the last equality in equation 5.8 is exactly the same as the last equality in equation 5.7. So what do we see here? We can see that this is a homomorphism because it preserves the structure of both groups. But this map is also bijective because G of theta and R of theta are functions of theta, and distinct elements in the domain are mapped to the distinct elements in the codomain. And one can think of, well, another way we can think of this is that the real and imaginary parts correspond to the x and y axes respectively, because when we multiply by this, so basically here it's quite clear because sine theta can be represented as the y-axis and cos theta can be represented as the x-axis polar coordinates. And what happens, since we're considering unit polar coordinates of a unit circle, this is simply the y coordinate and this is simply the x coordinate. And here, when we multiply by the ket, what happens is we need to multiply I to the y unit vector and the x by 1 of the x unit vector. So the x is real and the y is imaginary. So this is another way of thinking about the structure. And you can also see this in the picture here. We can see that the x-axis is the set of real numbers, but the y-axis is the set of imaginary numbers. So this is the nice thing. So now that we've talked about homomorphisms and isomorphisms, let us talk about some applications in physics. So let us look at one crucial example in physics. So maybe multiple, actually, we're doing two, but I don't know why I said one. But when deriving the electric field of an infinite sheet of a uniform charge density, we use Gauss's law because there's translational symmetry. But translational symmetry is even more fundamental when discussing conservation laws, as the energy and momentum conservations, basically energy and momentum are conserved when the Lagrangian is either time or coordinate independent. And that is, they have no space, they have basically, when they have this kind of independence, they have time and spatial translation symmetry. And this is a consequence of Noether's theorem, which states that every continuous symmetry corresponds to a conserved quantity. Therefore, we can use group theory to generalize these symmetries, as these continuous symmetries form an infinite group or a continuous group. So let T of A be e to the a dot the vector. Basically, this is the gradient. So this is an operator when acted upon. X translate the vector by a. So let's do this. So let's act this on some arbitrary function of x, and this is basically the Taylor expansion of e to the a dot the gradient. And then if we act this on x, we just get f of x plus a, because this is the definition of the Taylor expansion expanded about a. So to see the symmetry properties, we have to show that TA forms a group under vector addition of the arguments. So let T be the set of translations of any arbitrary vector. That is basically the translation of any vector here. So let the composition operator dot be defined as T dot a to the m. So basically what happens is this will make AL plus AM. This is essentially a homomorphism, but the homomorphisms is simply the scalar product between the two translation operators. Now, let us first show that it satisfies the closure property. So to do so, suppose that two vectors AL and AM are in the there are two vectors AL and AM. So if so, that there must exist two translation operators, T of AL and T of AM must be in this the set of translation operators, and the composition of the two translations should yield another translation operator. So T of AL dot T of AM is equal to T of AL plus AM, which is some other vector AN. So let's say AL plus AM is equal to AN. And since T contains the translation of any arbitrary vector, then T of AN is in the set T. Hence, this is closed under the composition operator. Now we need to check associativity. And this is quite simple. We do this. So basically, let's consider AP, AQ, and AR, the translation operator of them, and we dot each one. So basically what happens is we find that a T of AQ dot T of AR, basically we add their arguments together. And then what happens is if we do this, the same thing, we add the final argument. And if we do the first two operations first, this should have no distinguishment between the two. And the reason for this is, once again, scalar multiplication is associative and scalar addition is associative. So this property is associative. And since AP, AQ, and AR are arbitrary vectors, this satisfies the associativity for any vector in T. So now we need to show that there exists an identity, and it is trivial to see that the T of the zero vector is the identity, because when, well, let us look back at the definition. So if A of zero is, if A is equal to the zero vector, it basically means t acted upon f of x is just equal to f of x. So t of 0 must be the identity because it leaves x invariant. So finally, we need to show that there is an inverse, and to do so, we consider two different vectors. So let's say t of ax and t of ay are in T, such that ay is the inverse of ax under this. So by that definition, t of ax dot t of ay is equal to the addition of their arguments, and this should yield the zero vector inside. And this can only happen if ay is equal to minus ax, or ax is equal to minus ay, and they must be inverses of each other under this. So since T contains the set of all arbitrary vectors, this should basically every single vector in the set should have an identity, should have an inverse basically. So as a result, T is a group under the composition operator as it satisfies the group axioms. Now we can also check that this is an abelian group because AL dot with AM is equal to AL plus AM, but addition is, vector addition particularly is commutative, so we can swap the order and we can find this is just AM dot AL. So this is an abelian, an infinite abelian group. So what's important about this is that T of A is not a symmetry in itself, but when acted upon, operators form a symmetry as it leaves the system invariant. So let us see the connection between the momentum conservation and spatial translational symmetry of the Lagrangian. So if a quantity A is conserved, then the time derivative is 0, meaning that it is constant in all time. Another way to look at it, it is the Poisson bracket. So the Poisson bracket with that quantity with the Hamiltonian must be equal to 0, where the Hamiltonian is just the total energy, and the Poisson bracket is the partial derivative of the first argument by the coordinate, and the partial derivative of the second argument by the momentum, and take the anti-commutator between the two. So if the Lagrangian is symmetric under spatial translation, then the Lagrangian is coordinate independent, which implies that the partial derivative of the coordinate x of the Lagrangian is equal to 0. This inherently implies that L acted on T of L is equal to, they're basically equivalent. So basically T must be the identity. And the reason for this is because we can see that T acted upon L is equal to L, and we add the higher order terms in the Taylor expansion. And the reason why this is equal to L, because partial of x of L is equal to 0, and the higher order derivatives must vanish. So this is what it means for something to be translationally invariant. So however, what is partial x of L? Well, since the Lagrangian is just the Legendre transform of the Hamiltonian, such that the Lagrangian is equal to the conjugate momentum times the coordinate minus the Hamiltonian. Therefore, the partial derivative of x with respect to h is equal to the negative partial derivative of x with respect to L, which is basically by Hamilton's equation. We know this is equal to this, and hence, since we know that this is equal to this, this implies that this must be equal to this. So the partial derivative of x with respect to L is simply the conjugate momentum. And from this, we can see that since we're considering x as, maybe let's say x can be any arbitrary coordinate, but if we consider x as, let's say, a linear displacement, then this would be the linear momentum. If x was an angle like theta, this would be the angular momentum. But from this, we can see that p dot is equal to 0, since partial x of L is equal to 0, which means that p is a constant in time, and hence is conserved throughout. And we can see a similar connection if we change this translation operator to t of small t. And we can see that, so basically, if the Lagrangian is time symmetric, we can see that the energy is conserved instead of the momentum, because the partial derivative of L with respect to t generates the partial h with respect to t, and h is the total energy. So this will tell us how the total energy changes with respect to time, which will be constant. So basically, if partial L of t is equal to dh dt or h dot, then this will be equal to 0, since partial L of t is equal to 0, and this means that H dot is equal to 0, so hence the total energy is conserved. Well, you may ask, why is this useful? Well, let us look at the Lagrangian for a double pendulum without drag. So this is a very complicated Lagrangian. So θ1 and θ2 are the angles of the first and second pendulum, respectively, with respect to the vertical axis. And m, g, and l, so are real numbers, are positive real numbers that represent the mass, acceleration due to gravity, and the length of the pendulums, respectively. So let us ask the question, what quantities are conserved? Well, let us look at the Lagrangian, right? So the key here is to use Noether's theorem and see what quantities are not present. So we can see that θ1 and θ2 are present. That means the system is not coordinate independent. Hence, there is no spatial translational symmetry. So there's no angular translational symmetry. So we know here that the angular momentum and linear momentum cannot be conserved. Now, what is actually conserved? We can see that the Lagrangian has no time dependence. And as mentioned before, if a Lagrangian is time symmetric, then the energy is conserved. So we know that here the energy is conserved. And this makes intuitive sense because I mentioned that this is the double pendulum system with no drag. And if there's no drag, the energy should not decrease with time. And then the subsequent question you may ask is, how do we modify the system such that these quantities are not conserved? Well, you can obviously add drag. And by adding drag, what happens is that you make the Lagrangian time dependent. And then what happens is when the Lagrangian is time dependent, then there's no time symmetry and there will be basically the energy will not be conserved. But another thing you can do is you can add a driving force, which also makes the Lagrangian not time dependent. Make the Lagrangian time dependent. And then basically what happens is the energy will also not be conserved. Now let us look at a more specific example in solid state physics, and that is I will sketch a proof as to why there's only 5 Bravais lattices in 2 dimensions. So let us define what a Bravais lattice is. A Bravais lattice is an n-dimensional lattice such that basically an n-dimensional Bravais lattice is an infinite array of discrete points generated by the set of discrete translation operations described by the following equation, where alpha is some real number and a is some primitive vector. So a primitive vector describes the vector between points, some maybe 3 points that can generate the other points, but they need not be orthogonal to each other. So to determine the number of Bravais lattices, we need to prove an important theorem called the Crystallographic restriction theorem. And well, let me state what the theorem is. Consider a crystal in R3 that is invariant under rotations by an angle theta equals 2 pi over n, where n is an integer around an axis. Well, n is an integer and theta is the rotation around an axis. Then the only possibilities allowed are 1, 2, 3, 4, and 6, with n equal 1 being the trivial case of no rotation. This is simple to see. If we set n equals 1, this is a rotation by 2 pi, which should be exactly the same. So this theorem also, so I talked about this theorem in R3. This theorem also works in R2 and can be generalized to Rn. And as a result, in higher dimensions, there are many more Bravais lattices. So let us consider the discrete set of translations. So z sub n is equal to basically the rotation matrix of 2 pi over n. And we can see that z sub n is a group as it is isomorphic to the roots of unity, the n roots of unity. But more interestingly, z sub n is a subgroup of SO2, where SO2 is a group of all infinitesimal rotations in R2. And we talked about this in a couple slides back. And one may ask, why do we care about Zn, as it is only valid with respect to an orthonormal basis, and the primitive vectors may not be orthonormal to each other? While this is true, there are 2 invariants of Zn, namely the determinant and the trace. The determinant, we know, since it is a subgroup of SO2, the determinant must be 1, and the trace must be 2 cos theta, or 2 cos n, 2 pi over n. So these are invariant under basis change. So in any lattice, it would be sensible to write how the rotations act on the primitive translation vectors given some basis vector. So although the primitive vectors are not orthogonal and of unit length, a rotation by an angle is a rotational symmetry of the lattice. And from this, the rotational symmetry is discrete. And one finds that, from this, if the rotational symmetries are discrete, one finds that Zn must map to each translation vector into an integer linear combination of the other translation vectors. So moreover, basically, more specifically, actually, we should say that the trace of Z of n must be k, where k is some integer. Hence, we have the equation 2 cos 2 pi over n equals to k. And if we solve for n, we get this. And in order to satisfy n and k must be integers, the only possibilities are k equals -2, k equals -1, k equals 0, and k equals 1 or 2. And this corresponds to 2, 3, 4, 6, and 1 respectively. So this means, but I guess the question you may ask is, what does this imply? Well, this implies that in R2, there are certain discrete rotational symmetries that correspond to a discrete translational symmetry of the crystal lattice. Well, the other question is, how does this tell us the number of Bravais lattices there are? In R2, there are 2 infinite families of point groups, namely the cyclic groups Zn and the dihedral groups Dn. Given that there are only 5 possible rotations under angle 2 pi over n for n equals 1, 2, 3, 4, and 6, there are only 5 cyclic rotations, cyclic rotation groups and 5 dihedral groups. This corresponds to 10 crystallographic point groups in R2. However, some of these are degenerate, and we find that only 5 of these groups are unique, and each of these groups correspond to a unique Bravais lattice. And here I will show you what these groups are. So basically, we have an oblique lattice. Basically, it looks like a rectangular lattice, but the points are rotated by some angle phi, which is not pi over 2. We have a rectangular lattice where we have basically it's exactly the same as this, but the angle between. So basically, maybe last time I didn't really explain what a primitive vector is. So these two are primitive vectors, but they're not unique, right? You can choose these two to be primitive vectors, these two to be primitive vectors, as long as the area. So basically, this is called a cell. If the primitive vectors generate an area such that the area is the same as something that we know to be a primitive, a set of primitive vectors, then the other primitive vector is also a primitive vector. So in this case, these two are the primitive vectors, and this is the angle between them. So if the angle between the primitive vectors are these two vectors are not pi over 2, then we get an oblique oblique lattice. Here, these two primitive vectors are separated by phi, which is pi over 2. This is a rectangular lattice, and we have a rhombic one where we have 2. Well, you can see there can be many discrete primitive vectors, right? It can be these two or these two, but here, basically, if phi is not equal to pi over 2, and it must be equal, or it must not be equal to pi over 2 or pi over 3. So it can't be these two, or it can't be these two combinations. The next one is a square. Basically, it's a generalization of a specific case of the rectangular lattice, where the two primitive vectors are of equal magnitude but pointing in different directions, and they're separated by pi over 2. And the hexagonal one is the most interesting one, as it is two primitive vectors of equal length, but they are separated by an angle not equal to pi over 3. So what does this mean? This means that I think this should be equal, right? Sorry, this is a mistake. When I generated this plot, I made a mistake. This should be an equal sign, equals to pi over 3. And what happens is, in a hexagonal lattice, wait, is that right? Actually, maybe don't quote me on this one. I'm not certain. I have to double check. But in a hexagonal lattice, I think. Sorry. Yeah, this is right, because I was going to talk about graphene, but graphene is actually not a lattice, because if I recall, graphene does not actually have a point in the middle. Yeah, sorry, my apologies. So this is graphene is not even a lattice, because a lattice has to satisfy some certain symmetries, and a graphene sheet only has symmetries in certain nodes. So my apologies. I was going to talk about graphene, but turns out hexagonal lattices are not, graphenes are not hexagonal lattices. So this. So basically, in short, this shows the power of group theory, because by exploiting symmetry, we eliminate all other possibilities of Bravais lattices, and we show that in 2 dimensions there are only 5 types of Bravais lattices. And even though in this lecture I did not talk about quantum mechanics, despite this whole series being about quantum mechanics, I've discussed group theory in depth. And what happened is I will discuss linear algebra next time. And I will make the connection between group theory and linear algebra and representation theory. And subsequently, when I talk about the algebra and the groups, we can talk about commutators and how we generate different physical quantities in quantum mechanics. But I've also, I guess this lecture can be thought of more generally as the beauty of group theory in physics. So I hope you've learned something, and I'll see you in the next one. Thank you.